Hello class 11. The topic for the day today is centripetal force and of course thereby centripetal acceleration, which we are going to discuss. And obviously we are going to derive relation for both centripetal force and centripetal acceleration. Now let us first try to understand what the centripetal force is. You've learned in class 10 also, and we've discussed in the last video also that the word centripetal means center seeking. Okay, so to say, centripetal force is a force which is always directed towards the center. At any point, you consider point A, you consider point B, okay, at any point the centripetal force is always directed towards the center. At whatever point on the path, circular path, the centripetal force is always directed towards the center, and thereby the name center seeking force. Alright. Now, how do we know there is a centripetal force, or so to say a center seeking force in the first case? Say you're whirling a stone is tied to a thread and of course you're whirling it. And this is the motion, say for example, of the stone is executing. At any point A, its linear velocity is given by this straight line. The linear velocity is along the tangent. Okay, and since we are talking about a uniform circular motion, the speed of rotation is a constant, remember, or so to say, the magnitude of velocity is a constant. So at point A also, at point B also, the magnitude of velocity is the same, v. Okay, now since they have different directions, okay, velocity being a vector, it should have a direction, and we've learned that the direction of the velocity is along the tangent. The direction of velocity at any point is along the tangent to the point. So at point A, the velocity is along this line, at point B, it's along this line. Now since the direction of the velocity is different, let us consider the velocity vector itself on the whole to be different. This is vector v1 and let's call this vector v2. And mind you, the magnitude of both v1 and v2 is v, which is the same value, remember. Okay. So at point A, if there was no force acting, if there was no centripetal force, okay, let's assume that. So if there is no force acting, according to Newton's first law of motion, we know if there is no force acting, then the body would continue, if it is moving, by the way, if the body is moving, it would continue moving with a uniform motion. Uniform motion meaning it would continue moving with the same speed and of course along the same direction, mind you. So if there was no force, or so to say centripetal force acting, then a body at point A would continue moving along this straight line, so to say. But since there is this inward pull, okay, since there is this inward pull, what happens is this body gets pulled inside and reaches over here. Now at this point the body actually would want to travel in this direction, along this tangent, another tangent, but what happens? Again, there also is an inward pull. The body gets pulled in the inward direction, and thereby the body, say for example, reaches over here. Again, at this point also, if there was no inward pull, or so to say, if there was no centripetal force, the body would continue moving in a direction like this, in this direction, so to say. But again, since there is an inward pull, okay, the body reaches this point. So at every point, at every different point that we've considered, what we see is the direction of the body is being changed. As if something is pulling the body from the inside, because of which at every point the direction of the body gets changed. Otherwise, if there was no inward pull, like I said, at any point the body would continue moving along the straight line, or so to say along the tangent to that particular point. So since there is an inward pull whenever a body is executing circular motion, okay, so that inward pull is what is referred to as the center seeking force or the centripetal force, because of which at any point the body goes on changing its direction. Okay, so that force is what is called centripetal force. Now we need to derive, okay, let me erase these stuffs now. Alright, so this is our point A and this is our point B, and say for example when the body moves from point A to point B in time delta t, the angular displacement of the body is delta theta. Okay, so delta theta is the angular displacement. Now, like I had shown earlier, at point A, the direction of velocity is along the tangent. Let's call this vector v1, or velocity vector v1. And at point B, the velocity vector v2. Okay, so let us name these points, the central point also. O is the central point, so A, O, B. Now, if delta t tends towards 0, then AB is a straight line. We can consider AB to be a straight line if delta t is very, very small. So, AB is small, of course. Alright, and AB, so to say, is the linear displacement. I can also call it linear displacement. Alright, now if I draw this velocity vector v1 over here, this is our v1, keeping its magnitude and direction fixed. I'm drawing the velocity vector v1 over here. Likewise, velocity vector v2 over here. So this is our velocity vector v2. Now, so I have drawn these two vectors or velocities in such a way that they are starting from the same point, mind you. Now, if I ask you what is the angle between these two vectors, velocity vectors v1 and v2, the answer will be delta theta. Okay, the angle between the two velocities v1 and v2 will be delta theta, the same as this angular displacement. Now, if you ask me why, now I don't know whether you've studied this in mathematics or not. OA is the radius of the path. Let me represent it by r. So OB is also r. Alright. Now these are the two radii, so to say, at the points A and B. And this velocity v1 is the tangent to OA. Likewise, velocity vector v2 is the tangent to OB. Now, whatever is the angle between the two radii over here, or whatever is the angle between two straight lines, so to say, the angle between the perpendicular to those lines will also be the same. Now, since v1 being the tangent to OA, this angle is 90 degrees. Likewise, this angle is 90 degrees since velocity vector v2 is the tangent to OB. So, whatever is the angle between OB and OA, the two straight lines, the angle between their perpendiculars will also be the same. You need to remember this. Okay? Now, if you don't agree with me, you can actually prove this also. You can show that, the angle between these two vectors is delta theta. What I can do is I can bring this v2 over here. So v2 over here, say this is v2, keeping its direction magnitude fixed. I've got v2 over here. Now, this angle between the radius and v2, this is v2 now, remember, is 90 degrees. So this angle is 90 degrees. So to say, O, that we call this M. So OMA is a right angle triangle. Try to understand this clearly. This is the right angle over here. This angle is delta theta. So what should be the value of this angle? The value of this angle should be 90 degrees minus delta theta. But again, OA and this tangent, they are perpendicular to each other. So if this angle is 90 degrees minus delta theta, this angle over here, that is the angle between V1 and V2, has to be delta theta. You can prove it this way. Okay, so I hope the proof is clear. That was just to give you the proof. So let me erase the unwanted part. Let me erase this M also, so to say. So this is our radius. This is my circular path. Alright, so coming back to the real topic now. If I draw, from V1 to V2. So, this displacement vector over here, the distance, so to say, between the velocity v1 and velocity v2, or rather, let me call this delta v. This is the change in the velocity from v1 to v2. Now, how do you find the change in velocity from delta v? How do you find the change in velocity from v1 to v2? Look at this triangle. We have vector v1 and vector delta v forming two sides of a triangle taken in order, and v2 is the third side which is in reverse order. Okay, so triangle rule of vector addition tells us that v1 plus delta v is equal to v2. Therefore, delta v is equal to what? v2 minus v1. So this is the change in velocity. So instead of delta v, I could have written v2 minus v1. Alright, so delta v, mind you, gives us the change in the velocity over here. Okay, so now, since delta t, we've considered delta t to be very small, so AB is a straight line. So let us consider it's a straight line. AB is a straight line. So this is our triangle OAB. Now see, in triangle OAB, this values are, okay, so to say, the two sides of the triangle has same magnitude. So to say, OAB is an isosceles triangle. And since this angle is delta theta, okay, and the sum of the angles of the triangle is 180 degrees, and this being an isosceles triangle, this angle over here, that is angle B, is 180 degrees minus delta theta divided by 2. Likewise, this angle is also 180 degrees, that is angle A is also 180 degrees minus delta theta divided by 2. Okay, because the two angles of an isosceles triangle are also the same. Likewise, check this triangle. Let me name this triangle PQR. PQR is the triangle. Okay, you only have to understand this, remember. So the magnitude of u1 and the magnitude of v2 is the same because we are considering uniform circular motion. So this is v, magnitude of v1 is v, magnitude of v2 is also v. So this is also, PQR also is an isosceles triangle, and the angle between v1 and v2 is delta theta. We have proved this. Okay, so this angle R is also 180 degrees minus theta, 180 degrees minus delta theta divided by 2, and angle Q is also 180 degrees minus delta theta divided by 2. So this also is an isosceles triangle, and we see that all three angles of triangle PQR and that of triangle AOB, it's the same. So to say, these are similar triangles. Now for similar triangles, AOB and PQR, what we can write is, what is the property for similar triangles? The property is the ratio of the corresponding sides, it has to be equal. So let us take this side OA divided by this side PQ is equal to this side AB divided by the corresponding side, which is delta V, so to say, or rather let me write QR for now. So we have this property of similar triangles. Which side should I erase? Let me erase this part. So from there I can write OA. What is OA? OA is the radius R divided by what is PQ? PQ is, so to say, the magnitude V. Let me write. Okay, the magnitude of the velocity PQ. It's the length after all. Which is equal to AB. What is AB now? AB is the linear displacement delta S. Okay, I forgot to mention where do I write? So delta S is your linear displacement linear displacement AB. Okay, this divided by QR. Now what is QR? QR is delta V. So this is what we get using the properties of the similar triangles. Okay, so let me erase this part also therefore. So dividing both the sides by delta t, what we get is R by V into 1 by delta t is equal to delta S by delta V into 1 by delta t. Now let me bring this delta V to the left hand side. So R by V, I hope you all are following. R by V into delta V by delta t is equal to delta S by delta t. Now what is the right hand side? Delta S by delta t. It is the rate of change of linear displacement with time, and that is equal to the linear velocity, or R by V into, okay, and what is delta V by delta t? It is the rate of change of velocity with time, and rate of change of velocity with time is what? It is the acceleration. Okay, so this is the linear acceleration over here, since it's the rate of change of linear velocity with time. So this is equal to V, and thereby we get A is equal to V squared by R. So this is the expression for the centripetal acceleration. Okay, centripetal acceleration, this is always directed towards the center. Now if you want to write centripetal acceleration in terms of your angular velocity omega is, we've seen yesterday that V is omega r. Okay, so you can substitute over here. This is equal to omega squared r squared divided by r. Alright, and thereby we can write, therefore A is V squared by r, or the centripetal acceleration is omega squared r. So these are the two expressions for the centripetal acceleration. Remember that, class 11. Okay, whichever you prefer, you can write this. Okay, but we want to derive an expression for centripetal force. Now once we've derived this, deriving the expression for centripetal force is no big deal, because we've learned from Newton's second law of motion that force is mass into acceleration. Now if m is the mass of the body executing uniform circular motion, then the centripetal force, that we call it F, is mass into acceleration, which is mv squared by r, or so to say m omega squared r. So this is the expression for the centripetal force, and this is the expression for the centripetal acceleration. Center seeking acceleration, center seeking force. So this is all for this video. Thank you.